In the last lab, we considered a special case of Newton's second law, that where the net force was zero, and modeled an object moving at constant speed. In this lab, we will consider an object with non-zero net force acting on it and examine the interactions between the various forces in the system's surroundings. Then, again using Newton's second law, we will model a non-zero net force in VPython. For my lab, I dropped an empty water bottle of mass 0.007 kilograms from a height of about 3 meters with an initial velocity of 0. The bottle was chosen because it had a relatively large surface area for its mass and would create a better model of drag. In my analysis, I chose to set the origin at the initial position with the bottle dropping in the negative y direction. The basic idea was to understand the various forces acting on the object and their interactions. I considered the forces of gravity, that on Earth, and also turbulent drag. In addition, computational models of the object's movement due to the various forces were created and then compared. Finally, we see once again Newton's second law correctly describes movements we can observe in the real world. To begin, I analyzed the video in Tracker. The extracted data provided the final time t, 0.8 seconds, as well as the final position. This data obviously accounts both for gravity and drag. Moving into the Python modeling process, the first model created did not take into account the positive force vector F drag. Here F net was merely F gravity. When compared with data from Tracker, we would expect to see this object hit the ground more rapidly. The next Python model does take into account the drag force. To find the B, the magnitude of the drag force, I used the formula -1/2 c times rho star times the cross-sectional area to get a good approximation for the value. I then plugged this into the Python program and approximated and found a better approximation using trial and error. Here's the new Python model with a few edits for the drag force. Instead of the estimate of 0.0025 for the B given by the formula above, I found that a value of 0.004 for B better approximated the final height value found using Tracker. This slightly larger number might also be a reflection of the fact that the bottle does not behave entirely like a sphere, which is the object officially modeled with the formula I found. The bottle also begins to fall slightly sideways, increasing the surface area affected by the drag force. This graph looks pretty similar to the model without drag, but that's because the object doesn't fall for a very long period of time and the drag doesn't really catch up with gravity yet. Here you can see the object's final distance from the origin for this time t, a value which is very similar to the distance found in Tracker. The data collected from the Tracker and both of the Python models was then compiled and graphed in Excel, and as you can see, the position graph for the model with only gravity does hit the ground slightly sooner than the other two, as expected. Here's a graph comparing only the Tracker data and the model data from Python with drag. As you can see, there are a few places where the data doesn't match up exactly, places where the Tracker data noticeably doesn't follow a smooth trajectory. These discrepancies are probably mostly due to my error in the Tracker analysis, or perhaps some to the turbulence caused by the object falling sideways. Finally, to discuss terminal velocity. When the magnitude of the drag force is equal to the magnitude of the gravitational force, the net force will become zero, causing the object to fall at a constant speed for the remainder of its journey. This does not occur in my experiment, as the object does not fall for long enough. According to my estimates, terminal velocity for this object is about -4.141 meters per second, and the object gets pretty close after falling for about 10 meters. The slope of the tangent line, or the derivative, of the position versus time graph should become linear, as it appears to do so here. In the graphs from my experiment, it's obvious that the object did not reach terminal velocity. The model without drag will never reach a terminal velocity because it doesn't have anything to cancel out the gravitational force. Finally, we can examine what would have happened if the object had been thrown downwards initially instead of being just dropped from rest. In Python, I changed the initial velocity vector to both -4, a value near the terminal velocity, and to -30 meters per second, a value considerably faster than the object would ever naturally fall. The position versus time and velocity versus time data for these cases was then compared. The terminal velocity would, however, be the same because the object has the same forces acting on it. The Python model data corroborates this theory. Thanks for watching.